Welcome all. This is the part 2 of the discussion on designing an extensible circuit breaker library. So let's dig in. So in part 1 we talked about in detail about the circuit breaker pattern and how it's applicable to microservices based architecture. Let's do a quick recap. Now in electrical circuits, the basic function of a circuit breaker is that it has to interrupt the current flow after a fault has been detected. Now, unlike a fuse, a circuit breaker can be reset to resume normal operation. Now, in software, we want to have something similar. What we want to have is we have a primary flow, which is invoked as part of the normal operations, and then we have a secondary flow or an alternate flow. Now, if we detect a fault with the primary, what we want to do is we want to switch to the secondary, and we want to invoke the secondary if primary has faults. The second important point is that once in a while we want to check if the primary is alright, and if it's alright we want to reset to using the primary. So that's like reverting back to normal operation. Now in part 1 we talked about how circuit breaker is applicable to microservices based architecture by considering Netflix, how circ- uh, something like a circuit breaker is very useful uh, in an application like Netflix. So now in this video, let's dig into the detailed design of Nitsita, which is the circuit breaker library that I have designed for C# and Node.js, and let's build it up from grounds up. A circuit breaker, we can consider it as a function of a primary function and a secondary function. The primary function is nothing but the primary source which we want to invoke. But if the primary is at fault, then we want to have an alternate source, which is nothing but the secondary function. Now, what this library also has to do is it has to prevent the repeated invocation of primary when it's at fault. Now, this can be done using a switch or a flag. I mean that's where we start. We can think of it as a switch or a flag. So let's consider the flow that we want, or which will allow us to do this. So given that the circuit breaker is a function of primary and secondary functions, when it is invoked, it has to first check if the switch has been flipped. By default, it won't be flipped. So thus it has to invoke the primary. It has to check if the primary results in an error, or maybe the time limits that's allotted for the invocation of for the primary to come back exceeds. If either of these conditions occur, that means the primary is at fault. Now if the primary is not at fault, then we just return the result. But if the primary is at fault, then the first thing we want to do is to flip this switch, then invoke the secondary, and then return the result. The next call that comes in will see that the switch has been flipped. Then without invoking the primary, which might be at fault, what it does is it just invokes the secondary and then returns the result. Now all the further calls are thus invoking the secondary and returning the result and avoiding the primary, which might be at fault. Now we don't want to keep on invoking the secondary for all the calls. At some point we want to check if the primary is still at fault. So thus we need a way to reset the circuit breaker. So let's consider that flow. So assuming that the switch has been flipped, now we introduce a new check. Is this decision is do we want to now probe if the primary is okay? If we decide that we don't want to probe if the primary is okay and we want to continue invoking the secondary, we just invoke the secondary and return the result. But let's say we do decide that we want to probe if the primary is okay, then we'll invoke the primary. Again, make a safe call to primary, check if it results in an error or if the time limit exceeds, and thus determining if primary is still at fault. If it's not at fault, then that means the primary is all good. We flip the switch to use the primary and then return the result. If not, if the primary is still at fault, then we just invoke the secondary and return the result. Now let's say primary is not at fault and we have flipped the switch. What then happens is the further calls to the circuit breaker will see that the switch has not been flipped and thus invoke the primary. Cool. So now we have a way to switch the circuit breaker when it's at fault. We also have a way to reset the circuit breaker if and when we determine that the primary is okay. Now we need to combine this flow and this flow into a single flow. Now this is my attempt at it. So it's quite simple. So we invoke the circuit breaker, and if the switch, by default the switch won't be flipped, we invoke the primary. If we determine that the primary is at fault, we come here. At this point we need to see if it is, are we probing? So if it's not probing, this is the result of a direct invocation, then we want to flip the switch. So we flip the switch, then invoke the secondary and return the result. So this is a bit complex. To recap, what, let's say we invoke the circuit breaker, we determine that the switch won't be flipped by default, we invoke the primary, but primary results in a fault. Right now this is the result of invocation of primary directly, we are not probing. So we want to flip the switch so that further calls do not come to primary. So let's assume the scenario where the switch is flipped. We have already switched the flip so that the calls are all moving to secondary. At this point, if we decide that we don't want to probe the primary is okay, then we just invoke the secondary. But if we do determine that the primary, we want to probe the primary, we invoke the primary. Now if the primary is at fault, at this point it comes here and says, okay, are we probing? Yes, we are probing. This call is the result of the probe that we introduce. Then we do not want to flip the switch, we do not want further calls to go to the primary because it's still at fault. So then we just invoke the secondary and we return. But when we were probing, we determine that the primary is no longer at fault, then we want to flip this switch so that the further calls go to the primary. So we flip the switch, we return the result. Now there are two important aspects here which I believe should be in the control of the application that's using the circuit breaker library. One is fault detection. Now what's considered as a fault is could be very application specific. Now application might say that okay, it's okay with us if there is a time limit exceeded for 3 times, but on the fourth time it wants to consider it as a fault, or certain kinds of exceptions may not be faults. So we want to provide an opportunity for the application to tell the circuit breaker library that whether we should consider an error as a fault or not. So that's fault detection. This is one aspect which we want the application to control. Now the second part that we want the application to control is is the decision about when to probe the primary. Should we probe the primary and when to probe it? The application knows best when the primary could be okay again. So it can decide whether to probe the primary probabilistically. So for example, once every x number of calls, or it can decide to probe the primary after x time duration since the switch was flipped. So for example, we know that the certain system takes certain amount of time to come back up after it's reset. We want to go back to that after it's been reset. So there are a number of uh, what we call these as probe policies. When to probe can be called as a probe policy. We can have a variation of a lot of these probe policies. So this is where the extensibility factor comes in. This is where Nisita provides the control to the application to determine when the primary is at fault, and also gives control to the application to determine when to probe if the primary is okay. So thus, we'll expand the circuit breaker library, circuit breaker function as we had defined earlier. We still have the primary function, which is a primary source, secondary function, which is the alternate source. Now we want another function which is fault. Now the application has to provide this function. Now this function is to determine if the error should be considered as fault. So what happens when the circuit breaker library Nisita is running is, whenever it encounters an error, it will call this function, pass the error to it, and ask the function, should I consider this error as a fault? The other function that the application has to provide to the circuit breaker library is should probe. So whenever this decision has to be made by the by Nisita circuit breaker library to check if it has to probe, it will invoke this function should probe. Now at that point, when the application gets the control, and it can determine to tell whether Nisita should probe the primary or not. Now as discussed earlier, we can have a number of probe policies. It could be probabilistic after x time duration after the switch was flipped, or let's say even after like n calls to the secondary. So these two functions which are provided by the application is what makes Nisita extensible. Now these policies are determined by the application. There are some further notes which and further points which aspects which Nisita has. Now what Nisita does is it maintains the latest n errors encountered in a circular buffer. Now this is to allow the application to enumerate these errors and to determine if the switch has to be flipped. So for example, it can, as discussed earlier, it can say last 3 errors were timeout errors, then it can decide to flip. This allows greater flexibility in terms of when when we can consider the primary is at fault. Now what Nisita also does, it is maintain certain stats. It maintains like the number of calls since the switch was flipped, the time when the switch was flipped. Now both these stats, what they allow you to do is it allows the application to define its probe policies. So for example, if you want to say that okay, after n number of calls, after 3 calls to the secondary, we want to check if the primary has failed. Now this stat will allow you to determine that. Or if you want to say after 2 seconds of operations, we want of invoking the secondary, we want to determine if the primary is all right. So this stat will allow you to do that. Now the library itself has been implemented for async-await functions, and I have a version that's implemented for C sharp, and I have another version which has been implemented in Node.js. Now the thing to remember about Node.js is that it does not provide you a way to interrupt async functions after a time limit has been exceeded. There is no way to stop an async function from running after certain time duration. There is no standard way to do that. So thus the Node.js version is a little bit different than the C sharp version, where it can only consider that the time limit has exceeded after the fact. So once it occurs, once the primary takes more time than the time limit, and then once it comes back with the result, the Node.js version checks if the time limit has been exceeded, and if it's been exceeded, it will then throw an error saying that time limit exceeded. Now the application can then determine if it has to consider this as a fault or not. Cool. So that's pretty much it. You can explore the code at GitHub nmgmdr nisita.js. There is a C sharp version as well, and there is a Node.js version as well. You are welcome to review the code, provide any suggestions. Thank you for watching.